Alright, tonight you have a delightful show full of fun facts, and if you think this is good, just wait till you get back to class because I have even better stuff waiting for you then. But we start with the redundancy that in the last lecture that you saw we went through this. We'll do it again very quickly, that capital L, the angular momentum of a system, lowercase l, the angular momentum of a particle, and that the sum of these would be the sum of r cross p. But after all, no, I just messed up. Let's presume that r is perpendicular to p, because I don't want to go back and fix this show. That p is equal to mv for each of the particles, and v is equal to omega r, and we put the r's together. I take the I off the omega because they all have the same omega, and finally we recognize, oops, a little short on space here, we recognize that this sigma Ri squared m is the same thing as rotational inertia times that omega, which is the same for each of the parts, that this expression for the angular momentum of a system, which we did much more with last time. This is a rather poor beginning to what I told you was going to be a wonderful lecture. Have a checkpoint for you. I have a disk. It's flat. It has dimension depth, but it's got planar surfaces, a hoop with nothing in the middle, and a sphere. And if you don't remember, you ought to go back to what the rotational inertia of those three are. It would be great, you ought to kick yourself if you go back, because you need to have those in your head. So promise yourself to memorize them. They all, do they say they have the same mass? All three objects have the same mass, and they spin about the axes of symmetry by means of strings. These forces are acting on strings, so they act perpendicular to the arm, and with the same force is applied to all of them. And you're going to rank them according to their angular momentum. After you are done applying that force for some period of time, which would be the same for all of them, and their angular speed, and you choose the answers. This fist thing was about a time when we were holding up fingers, and we'd run out of fingers here, so the fist distinguished from the other. But you can just, go ahead. You circle the one you like on your worksheet. This conservation of angular momentum, here's where it starts to get fun. These are sort of applications of that idea that this person takes this angular momentum and by pulling in his arms changes his I. So this is the initial rotational inertia of the speed skater, and then he changes it to a smaller I. But because there is effectively no external torque, that we get it so that it's minimal, the angular momentum would be conserved, and so when the rotational inertia gets smaller, the angular velocity gets bigger and he speeds faster. The same way with the diver or gymnast, but he's rather dressed much more like a diver, I think, that they change their rate of spin by pulling into a tuck or stretching their body out to speed up and slow down their rate of turning. This represents a satellite in space, and again, the changing the orientation. Suppose there is a telescope that I want to point at a different spot in the sky. I got a flywheel inside the telescope, inside of this spaceship, and I cause it to spin, and that's going to be an internal torque. That spaceship will torque the flywheel, so the flywheel will torque the spaceship. Well, if it starts off with no rotational inertia, and then you torque the flywheel, which is going to torque the spaceship, then they will both gain angular velocity, and you wait until the spaceship has turned to point the way you want, and then stop the flywheel. So you apply a contrary. What way were we going? We were pushing it that way. I'll push it this way to stop the flywheel, which means I will push the spaceship the other way, stopping its rotation, and they started off with omega of both of them 0. They will end up with omega of both of them 0, but now pointing in a new direction. Again, I'd say an application of this idea. But look at these pictures. Here you have a frisbee. What could be cooler physics than that? And the point being made here is not changing your rate of turning using angular momentum conservation, but this time stabilization. That we give the frisbee a spin, or here, this satellite that's about to be launched, we spin it as we send it forth, and that causes it to have a very large angular velocity. For both of these, if they're spinning fast, a large angular momentum, as well as angular velocity, but the angular momentum was what's important to us here. If these get perturbed, the wind blows, or somebody taps it with their finger, that's going to be an external torque. Something pushes on this to cause it to be externally torqued. That's going to cause a change in the angular momentum. But if it's spinning slowly, then the final angular momentum will deviate greatly from the initial. However, if it is spinning fast, has a large angular momentum, then that same torque will cause a change in the angular momentum, but the effect is going to be minimized. The frisbee maintains approximately the same orientation, and the orientation of a frisbee is important because of the aerodynamics. The satellite's orientation is very important because we want it to point someplace. I hope you follow this. I think it is a very, very rich idea, and I will show you the coolest application of this ever when you come to class tomorrow. Okay, another checkpoint. We got a beetle. It's a rhinoceros beetle, if that freaks you out, on the rim of a disc. This is a lazy Susan. I don't know about you, don't got no rhinoceros beetles on our lazy Susans. The beetle, usually it's a cockroach, but the beetle crawls towards the center, and want you to consider does the rotational inertia increase, decrease, or remain the same? Does the angular momentum? Does the angular speed as that rhinoceros beetle crawls from the rim towards the center? Go for it, you smarties. Now, a puzzlement. Folks, take the time to be awed by this experience. Here I have two merry-go-rounds, and there are people standing on the edge of the merry-go-round, and there's a long pole, and person at A shoves the person at B and gives them a push, a force in this direction, which causes this person to accelerate in that direction. They get a torque that makes them accelerate. They start spinning this way, and so they gain, both of the wheels were stationary initially, and he gains an angular velocity, an angular momentum. But of course, if A pushes B, then B pushes A, which produces a a torque which makes this one spin this way. What is the direction of this angular momentum? What is the direction of that angular momentum? Ah, isn't that beautiful? They cancel one another out. This was an internal force here, and so angular momentum is conserved. This is boring, Mr. Houghton. Well, just hold on to your seats. Now I take the same two merry-go-rounds and I have the people standing right next to one another here. And person A gives B a shove, doesn't even need a pole to do it with that way, which pushes on B, produces a torque and makes B start spinning this way. But of course if A pushes B, B pushes A, which makes A start spinning that way.
Yeah, sir?
Take your right hand. What is the direction of this angular momentum? And what is the direction of that angular momentum? And I hope you are freaked out because this thing had an internal force and it gained angular momentum. Why wasn't angular momentum conserved in this case, whereas angular momentum was conserved in this case? That's crazy. You have to have an external torque to create angular momentum for a system. What's going on? I await your telling me tomorrow. Here is a problem that's kind of a boring problem, but I just want to make sure that we're up to speed on doing these. This is problem 26 from the book, 2 kilogram particle, that the x velocity and y velocity of that 2 kilogram particle are given, and its location at this instant is this location. And they ask what is its angular, and I suppose those are in meters, what is its angular momentum relative to the origin? And I hope you could do that. Why don't you take a moment and do it? And then I'm going to pull the answer onto the screen. And you would do r cross p. The r vector is from 0 out to here is 3i minus 4j. And the momentum vector, the p vector, would be the mass 2 times the velocity, which is 30i plus 60j, and then just do a cross product and you get 600k. At least I hope you did. Then they ask what is the angular momentum relative to not the origin but -2, -2. And it shouldn't be a great stretch. After you've seen this, it should be very easy. I hope you've done it already because we're pulling it onto the screen. That the r vector now goes from -2 to 3, which is 5i, and from -2 to -4, which is -2j. The velocity is the same, the momentum is the same, and this time you get 270k, 720k. Just using that cross product and believing in it. That was the point of that exercise. All right, last bit of cuteness. Here is a yo-yo that normally you can't see the axle inside the yo-yo. There's a string wrapped around it that comes out of the yo-yo. If you pull straight up on that string, how does this yo-yo move? And I would like you to actually get an answer to that and put it on your worksheet. Now if you pull here, how does the yo-yo move? And I hope I'm going to go through the analysis. You ought to finish with those two questions before you listen to the rest. What are the forces acting here? Well, you've got that string pulling up. You've got a weight. There would also be a normal force, both acting through the center of mass. And here at the floor, there's going to be a friction. But what direction is that friction? Well, when you pull up here, that produces a torque. which tends to make this wheel turn. It's going to turn that way, which means it's going to move relative to the floor that way, which means there will be a friction force in this direction opposing that motion of yo-yo relative to floor as it rotates, and that friction force will cause the yo-yo to move to the left when you pull up. No surprise, perhaps. Again, if we free body this one, we have the normal force and the weight, neither of which produce any torque. But look at this pull. This time the pull is going to, is it the same? Yeah. The pull is going to produce a force in the same direction. The friction is going to be the same direction. It's going to oppose the relative motion. But if this friction is smaller than that force, then there's going to be a net force in this direction. The thing will move to the right. Whereas here, there is no force to the right. It will definitely move to the left in this case. All right. So, depending on how you pull the string, it will go one way or the other. And the analysis of this, I think, is rather rich. That here I have drawn the object again. I think we need it a little bit lower on the page so that you can see it. That little r can be the radius of the axis of the yo-yo. It's not a very symmetric yo-yo. Capital R is the radius to the outer rim of the yo-yo. Theta is the angle you're pulling your string at, neither straight up, that would be a theta of 90, or straight horizontally, that would be a theta of 0. And you're going to have this friction force going off to the left. We've already analyzed all of that. Then, having gotten those forces, let's go to Newton's second, and we have the torque is going to be the R, this arm, crossed with that force, they will be at right angles to one another, minus this torque, which will also be at right angles to one another, and that's going to cause the rotational inertia to have its angular acceleration. But horizontally, the translational forces, you have this component of the force, F cos theta, and this friction force. And that's what's going to cause the translational acceleration of the disk. And it's very important that we don't pull so sharply that we make it skid. It's going to roll without slipping. So there will be this correspondence between A and alpha. I will take the value, I will take this fact that F cos theta minus MA is equal to friction, solving here, and I'll put that in for friction here. So I have R cross F, but I said they were at 90 degrees, and R cross this quantity F, again they were at 90 degrees, is equal to that. And then if we take and put the A's together, and doing the fact that so you have the RF and the RF cos theta, but then I'm going to move the RMA over to the other side, it becomes plus. But of course A is equal to alpha times R, so I pull a common alpha out, and you get an extra R here, so it becomes R squared times M. There we have the sense of how it's going to accelerate, which was different for the two different pulls. That if this quantity over here is negative, then alpha will be negative. That would mean into the page, that would mean an angular acceleration this way. It's going to go to the right. If this quantity over here is positive, then alpha is positive, which means it comes out of the page, which means you have an alpha going this way, which means that it's going to be going, no, to the right. That one's to the right. I don't know. Don't listen to me. If for this to be positive means for cos theta, notice we have a common f there, cos theta would have to be, for it to be, if that was greater than r over capital R, then you get a negative quantity here. Now let's get this straight this time. A negative quantity means a negative alpha. That means my thumb's pointing in. The acceleration is this direction, which means, gotta see a picture. It's accelerating that way, which means the net torque is into the page, which means the R cross F, the net force is going that way. It would roll to the backwards, as I say, to the left. If you get cos theta equal to r over r, then you get a 0 here, and there shouldn't be any acceleration. And if you get the cos theta less than r over r, then this becomes a positive quantity. You get a positive alpha. Turn this around, and this time that's an alpha coming out, r out. I get the thing rolling forward. Here's another picture. Here's another picture which we'll put over top of stuff. And this value theta that we were looking at, that cos theta, but here is lowercase r and here is capital R. So cos theta, this after all would be a right angle, because this, if this line is going right up next to the axis, then that would be a right angle. It would be tangent to that circle. Then this is a right triangle, and r, here's theta, there's theta. Convince yourself that this theta here is the same as if you did it down here at the ground, and then that's the complement of theta, and that's the complement of the complement of theta, so that's theta there. That the cos theta is equal to this quantity over this quantity, the hypotenuse, and so the magical moment at which between rolling to the left and rolling to the right is when you get that string going so that it acts right tangent to the inner axle. And we'll have a chance to play with that in class. I hope that was worth your time. That's it for today.